So we are still talking about enthalpy, and this is useful stuff. I mean, how much heat will a reaction give off? You got to be prepared for it. Well, how much heat is necessary for a reaction to proceed? Those are all useful things. Well, but what about also like this bottle of water, right? How much heat does it take for it to warm up to 50 degrees Celsius? Or how much heat will it give off to cool it down to 10 degrees Celsius? You got to suck out the heat. So these heat problems, there's going to be several that we're working on, right? We're also going to work on another type of heat problem where we're going to determine the enthalpy for a reaction. We're going to actually calculate it and write a complete thermochemical equation. So there's something that we're going to start talking about, and that's heat capacity. And I don't know, we've all eaten pizza, and if it's got a lot of tomato sauce, you don't blow the crud out of it. If it comes right out of the oven, if you don't blow on it a lot, it just ends up burning the top of your mouth every single time. Why? Because tomato sauce is really thick. It's got a very high heat capacity. In other words, you put that thing in the oven, you make it, you put it in the oven, it takes a long time for that tomato paste to warm up, to heat up, because it has a very high heat capacity. It's going to take a lot of heat just for it to go up 1 degree Celsius. That's a very high heat capacity. So it's going to take a long time for it to heat up. It's going to take a long time for it to cool down, things with high heat capacities. So with heat, we have two symbols now, Mia, that we're going to start using for heat. What are they? What two symbols? There's a hint on this page. Triangle is change. Anybody else? Q. 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 Okay. Try to read that. These assigned readings, yeah, bold words are nice, but you got to try to read it more carefully. So these things should be more fresh in your mind. There's another one for heat. H. Except we're supposed to say enthalpy or delta H, right? So there's our two. The units. What units are there for these two symbols? Ashley, what would be the units for this, for heat? Joules. Okay. Joules, very common for both of them. Now, but for enthalpy, very often you're going to see probably more common kilojoules, but it's still heat. And then if it's a thermochemical equation, right, if you've got some reaction, reactants go into products, and you have a delta H for it, it's not just kilojoules, it's kilojoules per mole. So enthalpy is a little bit confusing, because enthalpy can, what's the enthalpy of this reaction? They just want the answer in joules or kilojoules. But if they want you to get the change in enthalpy for a reaction, then it's kilojoules per mole. So I guess the terminology helps. I mean, when you have a reaction and a delta H, and that delta H is always in kilojoules per mole, they call that a thermochemical equation. Thermochemical equation. So in writing a thermochemical equation, you need the reaction and you need a delta H. And the delta H is always in kilojoules per mole. Okay. And that's going to be important. That's going to come up and bite us in the back if we don't remember that. Emily, when heat is produced during a reaction, so heat's being produced, it's a product, the system, in other words, the container and the surroundings, it will heat up. Okay? And the calculated heat, Kendall, because you're going to have to put the sign on these heats, these joules. The heat, you're going to put a negative sign or a positive sign on that. If the heat's produced, the system heats up. It's negative. Good. It's negative. Exothermic, negative heat. Heat's being lost. That's why they put the negative sign on there. Kenneth, when the heat is absorbed during a reaction, the system will cool down. Hold it. Yeah, the system will cool down. Yeah, because it's sucking up the heat, right? Yeah, he's right. All right, it's got to be sucking up the heat from somewhere. The calculated heat is positive. All right, so that the system, everything surrounding your little container there, the reaction, it's got to suck up the heat from somewhere. So everything's going to cool down. It'll cool down. Okay, several categories of problems that involve heat. So I count 1, 2. What happened to my 2? Here's my 2. 3, 4. Looks like that's it. Okay. So there's 4 types of problems that are going to involve heat. And it looks like the first 2 involve an equation. So Paul, what did we say Q is again? Heat in units of kilojoules or joules. Okay, so there's our heat. So equations 1 and 2 are going to give us 2 equations to get heat. Let's look at equation 1 first. Tanya, what's this ms and delta T? You recognize any of these?
That's the reaction.
What's that? ms or delta T?
T be temperature.
Yeah, T is going to be temperature. And that change in temperature, right? So what could you say? T final minus T initial, or all right, the change in temp. Okay. And then how about M or S? Lauren. Yeah, mass. M is going to be mass. Now, what these equations 1 and 2 are for, equations 1 and 2 are for the pizza problem. How much heat is going to be given off by this tomato paste? How much heat is this tomato paste going to absorb? You're talking about a substance, something, a kettle, gas. In other words, it has to be a substance, and we're talking about heating it up or cooling it down. How much heat is that going to take? That's what this equations 1 and equation 2 are for. Let's get the Q to heat up or cool down this object. So M is the mass of that object. Exactly. And I'm going to leave out units for now because it all depends on what little s is. Does anybody know what the name is for little s? It starts with specific heat. S is specific heat. Specific heat. Okay, so it's just a constant, and it's going to be a really big number for something like tomato paste. But let me give you, so they have to give you that number. And let me give you an example of one. Like water is 4.184 joules per gram degrees Celsius. That's an example for the specific heat. So all these substances have different specific heats. The bigger they are, right, the more heat it's going to absorb for every degree Celsius. So if they give you this little s in this problem manual, your mass had better be in what units if you're going to use this equation? Grams, right? So I bet you there's going to be some converting. They're never going to give you the mass in grams. They'll give it to you in kilograms or something. But get the mass in grams. Your temperature, Lorena, that temperature change better be in what units? Celsius. Okay? So just make sure your units are consistent. So that's equation 1. Let's take a look at equation 2. Alyssa, Q is still our heat, but you recognize either of the other two? Well, heat could be in calories. That could be a unit for it, or joules. That could be a unit for heat. Yeah, there's one, change in temp. So since both equations 1 and 2 are for some substance, right? How much heat is it going to take to warm this object up to 20 degrees? How much heat is this object going to release? S is the little parameter that you use for that object in equation 1. C is the parameter that you use for that object in equation 2. So they have to give you these things. What's the name of C? Heat capacity. capacity. Very good. Heat capacity. And those numbers could be all over the place. Let's say the heat capacity is, they give it to you and they say it's 10 joules per degree Celsius, right? It's kind of an easier equation to use. So your delta T would just have to be in Celsius, right? And you get your answer in joules in that case. So I'm just giving you an example. Okay, so that, or you could solve for C, either case. Okay, so there's our first two. Third type of problem. Calculations that involve an incomplete thermochemical equation. So, Connor, what did we say a thermochemical equation is again? Has what two things? Changing enthalpy. Has a delta H, and it has a reaction. You have a reaction and the delta H, a change in enthalpy. That's a thermochemical equation. You need both. So that's what equation 3 is all about. It's saying, okay, we're going to give you the reaction, but we're not going to give you what the change in enthalpy is. You have to calculate it. So that's the third type of problem, is writing these thermochemical equations, making them complete, getting a number for that delta H. And I still think this is the key, Megan, to getting this question right. What are the units for this delta H? Who am I picking on? I'm picking on Megan. Yeah, what are the units? Yeah, very often kilojoules. They like kilojoules. But kilojoules per mole. So units, I really think, are an equation of themselves. Like density. You divide the mass of the stuff by the volume of the stuff, you get density. Just like enthalpy. Divide the number of kilojoules by the number of moles, and you'll get enthalpy. Or number of joules over the number of moles. You get enthalpy. It'll be in joules per mole then. So if you remember that, I think you can see a game plan to calculate that delta H. All right? We've got, Giselle, this is just a pretend problem. We have 12 grams of iron, and it's going to react. 69 kilojoules of heat's produced. What is the change in enthalpy for the below reaction? What would you do?
69 kilojoules over you convert the 12 grams of iron to moles.
Perfect. That's exactly right. You hear her? She's going to take those 69 kilojoules, and she's going to divide it by, 12 grams. What is iron? I can never see this stuff. 55.85 about. What is that? 12 over 55.85. I get about 0.215. Exactly. Divide the number of kilojoules by the number of moles, and we'll have our answer. And that number goes right there. So, about 321. Okay? So that's the third type of problem, where they're going to say, okay, you finish the thermochemical equation. And they're going to give you the information you need to do that. The kilojoules divided by the number of moles. Okay, the last type of problem that involves heat. Calculations that involve a complete thermochemical equation. Well, if it's complete, then you know what, Rebecca? What two things do you know if you have a complete thermochemical equation? You would know the what and the what. The thermochemical equation has two things. What were those two things again? The reaction and its heat, enthalpy. So you know the reaction and you know the heat. So we use our answer from 3. So let's just 321 kilojoules per mole. Okay, so here's our thermochemical equation. Third fourth type of problem. Here's the sample question. 29 kilojoules of heat evolved. How many grams of iron reacted? Let's see if Mia has a game plan for this. How did I get to you all back already? I'm skipping people somehow, Mia. That's all right. Life isn't fair. Do you see a game plan to do this? Anybody help her out? If I would have, think of the mole bridge idea, because this enthalpy is just another part of the mole bridge. So if we had 29 kilojoules, what mole bridge, right? This is what I envision. I envision 29 kilojoules, and I do this whole dimensional analysis thing and I do whatever I got to do until I end up in grams of iron. And I'm starting with, instead of it being a chemical, I'm just starting with heat. So it's a mole bridge to convert from one substance to another, or one thing to another. What would be the first thing you'd use, Steph? What would be the first ratio? Yeah, so the 321 kilojoules has to go where? On the bottom, otherwise it's not going to cancel. The question is, what goes up on top? Yeah, the 1 mole of iron. Or half mole of oxygen, or 1 mole of iron 2 oxide. But we're after iron, so we'll pick the iron one. And it's just the coefficient out front. And then we're back to our molar mass of iron, which we said was 55.85. Whoop, wrong way, right? In a mole of iron, you have 55.85 grams of iron. So 29 divided by 321 times 55.85, about 5. 5.04 or something, depending on how many digits you want to carry. Okay? So those are the 4 types of problems. The first 2 involve just calculating heat for objects, where they give you the specific heat or the heat capacity. And then the third type is writing complete thermochemical equations. And just remember, delta H is kilojoules over moles. And the fourth type is getting heat when they give you a complete thermochemical equation. And just remember the mole bridge idea. Okay? So let's go to the board and see if we can do a bunch of these, and then we'll call it a day, and you can enjoy your weekend. Let's try the first one. What is the enthalpy change to burn 35.8 grams of ammonia? What is the enthalpy change to burn 35.8 grams of ammonia? Kendall's gonna be lazy today? I think it's better. But if you explain it to somebody else, it's going to be stronger for you. So in this first one, you want to really start with what and end up with what units for your answer? You want to go from grams of ammonia all the way to kilojoules, right? Because remember, enthalpy is just another word for heat. Heat, right? So start with the 35.8 grams of ammonia. Do you recognize this is that last type of problem where they gave you a complete thermochemical equation? So you're just going to use the mole bridge idea to get where you need to go. Let's see if that's what everybody else gets. I don't see anything wrong with it, though. Yep. Yeah, so you're going to have to use the mole bridge, those two.
With the 4, are we going to multiply and then have that number? Like 4 nitrogens is 4 hydrogens? Or is this going to be
No, molar mass of ammonia is just N and 3 hydrogens. I think that's 17, isn't it? Because 14 and 3 would be 17.
Oh, I just multiplied by 4.
So did anybody get an answer for this first one? Oh man, really? The sign of the devil for this one? Really? Negative 666? Oh, that's better. Okay. Do we keep the negative sign on there? Yeah, because it's giving off that heat. That's a negative kilojoules. Right. So if you got it, try the next one. Did you get it to work?
Yes,
Okay.
I just didn't know that this had to be a 4. I thought it was 1 over the kilojoules.
Oh, yeah, it's from the mole bridge. So it has to be whatever's in front of the compound you're interested in. If we were interested in oxygen, it would have been a 3.
Okay, yes.
How many grams of ethanol are required to provide 358 kilojoules of heat? Yep, good, keep going. Did you figure it out?
Mm-hmm.
Okay. I think write down the substance, because that'll help you to know what the next step would be. Did you get an answer?
Yeah, but I was going to ask you, if you're dividing by a negative, how can
Oh
be
yeah,
a
you can't have
gram?
negative grams, so you just erase the negative.
So it's just a
So you got
math.
about 13.3. Yeah, good. And then you got to get the molar mass of that thing. These guys got about 10 though, Alyssa. Oh, you guys both got 13. They both, 2 people got 13, Connor. Oh, we have 10 and 13. Well, you're supposed to figure that out.
Oh. That's how I got 13.
You got 13 too. What, 24, 30, 46, 47 about? Yeah, about 13.6. So the 13 one was right. And like Alyssa noticed that you have it's really negative 13.6, but you can't have negative mass. You just kind of erase the negative sign. Right? Yeah, just erase the negative sign. You can't have negative grams. Okay, so if you're good with that one, let's try the iron skillet. So does anybody have a game plan for number 3? Okay. Emily's got an idea. She says use Q equals ms delta T. I like that idea. You have everything you need to use that equation. Just watch your units. Just be careful with the units.
They give me joules over grams per degree Celsius.
Yeah.
So it would be joules for specific heat.
Yeah, so specific heat. S is that 0.449 joules per gram degree Celsius. Mm-hmm.
Is the change always positive?
No, change is always final minus initial. That's what change always is. Sometimes it'll be negative, sometimes it'll be positive.
You got a negative, right?
Yeah, negative 1.57.
You know what's kind of a little bit easier, I think, is like the 1.28 kilograms. Wherever you see kilo, just write 10 to the third. And then you have to worry about this, because you can put this in your calculator, the scientific notation stuff. It's kind of faster and easier. You don't have to worry about moving decimal points and all that stuff. And it has to be grams because that's what your specific heat is in. What'd you get, Connor? You get an answer?
-90231.
-90231. With the units of joules. Did anybody else get -90,231? Okay. Is the negative sign right?
Yes.
Because the temperature's going down. Heat has to get sucked out of there, released. Good. Good. I think 4 is, yeah, 4 is a good one. 4 is about as hard as it gets. You can do 4, you're in good shape. Oh, -90,231. See if you can knock out 4. See if you can get a game plan to figure it out. Manuel, got a game plan for this? All right, it's not a straightforward problem. Paul, Kenneth, anybody got a game plan for this?
The first part you use the temperature.
C delta T. Yeah, because they gave us heat capacity. So it looks like you could be using that equation Q equals C delta T in some part of this solution. Right?
You have to convert the 23.6 grams to
Good. Okay. Did you hear what Alyssa's saying? So combine your two answers here. Get Q equals C delta T. Because remember, delta H is always, just remember the units. Delta H is what over what? Enthalpy for our thermochemical equation. Kilojoules over moles, or joules over moles. It doesn't matter. It has to be joules over moles or kilojoules over moles. It's delta H. So that's how you get those two parts. Combine what Kendall said and what Alyssa said. This is going to be, I'll just stick with kilojoules since that's what we've been using. Right? So I think Kendall said, okay, use Q equals C delta T to get this. And then Alyssa said, hey, that is 23.6 grams of, well, you got to get it in the right units, though. 23.6 grams of calcium chloride. Just convert it. Just convert it into moles. And then divide the two, and you'll have your enthalpy. Does that make sense?
But like for that one, since it says joules over Celsius, can we not do kilojoules? Or we have to convert?
Oh, yeah, it's up to you. You can leave this in joules.
Yeah.
It doesn't hurt anything.
Okay.
It's just, that's how I introduced it, so I left it that way. Because you're right, it's extra work to go to kilojoules. You just leave it in joules. So we could make our life a lot easier. Let's just erase the K.
That's too big of a number.
So you got a 8448. What's your units?
Well, this one here.
You'll have moles on the bottom.
Joules per mole.
Okay, yeah, joules per mole. 8448. Let's see if anybody else got that. Did anybody else get 84? What did you say? 90? 8498. The final answer? 8498. What'd you guys get? I'm trying to get a consensus. Kendall, what did you get for your change in enthalpy? What did you get, Stephen? 80,932. Well, that's pretty close. 913.
Got the same thing.
You got that too?
Yeah.
80,913?
Yeah.
In a joules per mole or kilojoules per mole?
Joules.
Joules per mole. It's like 3 people got this one, so it's just probably some rounding or something. All right, you should get that. 80,913 about. Is it supposed to be positive or negative? Is the temperature going up or is it going down?
Going up.
Temperature's going up, so it's absorbing heat or releasing heat?
Releasing. It's releasing.
Temperature's going up.
Yeah.
So it's absorbing it, right? It has to absorb a lot of heat to go up. So that should definitely be a positive sign, right? Or you don't even have to write anything. It's just leave it alone. So if you got it, go on to the part B.
Okay, so like ours, on like our example 4, it says there's like a second part.
Oh yeah, what's your second part?
It says what is the change?
Yeah, it's the same thing. I just made a
Okay,
little
so
B.
okay.
I just made a little B.
Oh, that's B?
Because we're all like getting different answers.
For the part A? 10,044. I think it depends on how many digits you carry out. Because I carried out a lot of digits. So I got 81,045. So I think it depends on the digits, right? If you carry a lot of digits in your molar mass and everything. So that's something to be careful of, I guess, to get the answers in the back of the book. Just carry a lot of digits, and then your answers will match the back of the book better. Like, look at my molar mass. I carried 110.98. And my moles, I carried to 3 digits. Okay. So in this last one, before we get out of here, you pretty much just start where? Start with the 1.2 moles of calcium chloride. And then whatever you got for your enthalpy for that reaction, just put it in. I got 81,045, so I have 81,045 joules in a mole of calcium chloride. All right. About 97,254. So if you get anywhere around 97,000, 98,000, 96,000, you should be good. Just carry more digits. Okay. So have a good weekend.